Okay, so in this video, we're going to talk about an ultrasound scan, and in this case, we're going to talk about A scans. So the A scan, it travels in a straight line, and it can be used to measure the thickness of bone. So we can, in this case, we're going to talk about measuring the thickness of a lens. So what you could do is that, well, for an A scan, you can measure the distance between the lens and the retina. Um, Now, as the transducer is here, um, the crystal inside, there's an alternating voltage applied to that crystal. So when the alternating voltage is applied to that crystal, it will contract and it will expand. So if you remember what a piezoelectric crystal, what does it do? So here, if you look at this diagram here, if you were to stretch the crystal, um, you would end up with a negative charge at the bottom and a positive charge at the top. If you were to contract, so if you were to squash it, the negative would be at the top and then you end up with a positive at the bottom. So if you were to contract and expand the crystal, you end up with a voltage, and it will be an alternating voltage. Right, so here's the transducer. It emits an ultrasound pulse. So here are the pulses. So it emits an ultrasound pulse. As it reaches the boundary, so as it touches the boundary, it gets reflected back. Some of it will get transmitted. So here, the loss in energy, as it reaches the boundary, some of it will get transmitted through, some of it will get reflected back, and that is why the energy will be lost. All right, so here there are four types of boundaries in this case. So the first boundary is at the front of the eye. So the front of the eye into the eye. Now the voltage is when the reflected ray reaches back to the transducer, and that records the voltage because the crystal will vibrate, it will expand and contract. That will read a voltage. So the ultrasound pulse, it reaches the front of the eye, reflected back. Because the crystal expands and contracts, that reads a voltage here. Now, some of the ultrasound pulse will go through the eye and it goes to the front of the lens. So there's the front of the lens. Now, the front of the lens, as it reaches the front of the lens, some will get reflected back, some of it will get transmitted. So because some of it gets reflected back from the front of the lens, here is the recorded voltage. And as you can see, the amplitude gets less and less because energy gets less and less. After it reaches through the front of the lens, some of it will get transmitted to the back of the lens. Some of it gets reflected back, some of it will go through. And this is the third line. And then the fourth line, because you've got a longer distance there, and so that will be the fourth line there. Okay, so how would you work out the distance of the lens? In this case, let's look at that here. So T2 is the time it takes for the reflection to reach the transducer. So T2 is the time for the reflection, it's the reflection of the ultrasound pulse after it hits the back lens. So that's the reflection. To work out the distance, you need to half the time times the speed of the sound in that material, the speed of ultrasound in that material. That will give you the distance from the front of the transducer to the back of the lens. Now T1 divided by 2 is the time it takes for the reflection after it hits the front of the lens. And because you want to halve it, because that's an echo, you multiply then to the speed of ultrasound, and that will give you the distance from the transducer to the front of the lens. So to work out the distance of the lens, you take away the two. So this, take away this. And then that will give you the distance of, that will give you the length of the lens. Okay, so as a recap, the A scan is a straight line ultrasound pulse that measures, either you can use it to measure the thickness of bone using this method, or you can use it to measure the distance between the lens and the retina. In this example, we have used this method to work out the length of the lens.